In this section, we're going to look at torque. We're going to use the Greek letter tau to represent it. So what is torque? Torque is a physical quantity used as a measure of the rotational effect of force. This is a physical quantity, used as a measure of the rotational effect of force. Rotational effect of force. Now let's see on what factors it depends upon. Suppose you have, let's say this lever pivots over here. Now it matters on where you apply the force. You will have more rotational effect if you apply a force at the edge than you would if you apply the force closer to the pivot over here. So it depends on the distance between the pivot and the point of application of force. The greater the distance, the greater the rotational effect of the force. You'll be more effective in opening a door if you apply your force at the edge than you apply it closer to the hinge. Actually, if you apply the force right over here, you won't be able to rotate it. So we can say that the rotational effect of force or the torque is proportional to the distance between the pivot and the point of application of force. Okay? Torque is proportional to the distance between pivot and the point of application of force. The point of application of force. Okay, so it depends on the distance. Obviously it depends on the force too. So let's say suppose we apply this force over here. Now let's decompose this force in two parts. This part and this part. Now obviously this force is not going to have an effect in rotating the lever. You cannot rotate this lever by applying a force parallel to the lever. So it's only this part that will have the effect of rotating the lever. Okay, so we can say that it depends on the component of the force perpendicular to the position vector of the point of application of force with respect to the pivot. Okay, so you take the component of the force perpendicular to this line over here, and that's what it depends upon. It doesn't depend on the horizontal component, it depends only on the vertical components. So we can say it is proportional to the component of the force perpendicular to the position vector of the point of application of force, with respect to the pivot. Okay, so let's say represent this by R, this distance between the pivot and the point of application of force. Okay, and let's say this is the position vector of the point of application of force. Now this angle over here is angle between force and this position vector over here. This is R over here. Okay, so we can define torque to be the product of this distance and the component of the force perpendicular to the position vector. Okay, so we can define torque. Therefore, torque can be defined as torque equals the distance between the pivot and the point of rotation, and then the component of force perpendicular to the position vector of the point of rotation with respect to the pivot. But this could be positive or negative depending on whether the rotation is clockwise or counterclockwise. So let me put this in absolute value. Okay, so this is the definition of torque. It is equal to the distance between the pivot and the point of application of force, and the component force perpendicular to this position vector, the position vector of the point of application of force with respect to the pivot. Okay, let me write that on the next section. So you've got torque equals R times F perpendicular. Okay, now in this formula, this is magnitude of torque, and R is distance between pivot and point of application of force, okay, and then of course F perpendicular, this is component of force perpendicular to the position vector of point of application of force, with respect to pivot, Okay, now we can write a little bit differently using the angle between the force and the position vector. If the angle between the force and the position vector is theta, then we have the following: F perpendicular actually equals the magnitude of the force times the sine of theta. Okay, you see that? This is the force, this is the magnitude of the force F. If the angle between the position vector and the force is theta, then this component over here is magnitude of the force times the sine of theta. So we can write the torque as, therefore, the magnitude of torque can be written as the magnitude of the force, the distance, times the sine of theta. Maybe it'll be easier to use this formula, right? So this theta is angle between the force and the position vector. Okay, so this will give you the magnitude of the torque. All right, now we have two kinds of rotations. Okay, it could be in this case, you see the lobe is going to rotate this way. That's a counterclockwise rotation. But also if you pull it down, it will be clockwise rotation. So we have to distinguish between these two kinds of rotations. So torques that cause counterclockwise rotation are taken to be positive, while forces that cause clockwise rotation are taken to be negative. So let's see the sign convention over here. Sign convention. Okay, torques that cause counterclockwise rotation are taken to be positive, while torques that cause clockwise rotation are taken to be negative. Okay, so this is the sign convention we're going to use. If a torque causes counterclockwise rotation, we'll take it to be positive. If a torque causes clockwise rotation, we'll take it to be negative. Okay, and then so we can use this formula to calculate the magnitude of the torque, and then we can determine whether it's positive or negative using the sign convention, which depends on whether it's clockwise or counterclockwise. Now let's look at some examples. Let's say we have this meter stick pivoted at its center. This is the pivot over here. Let's say this is maybe 1 meter. This is 1 meter over here. And let's say we have this force acting over here. Let's say it's 10 Newton. Okay, so the question is calculate the torque. Okay, calculate the torque. Okay, so what do we have? This is our pivot. So the distance between the pivot, this is the point of application of force, and the pivot, the distance from the pivot and the point of application of force is 1 meter, that's R. So R equals 1 meters. The magnitude of the force is 10 newtons. That is 10 newtons over here. And this is the angle between, you see this position vector over here, and the force, which is 90 degree. Okay, theta equals 90 degree. Okay, now in this case, well, you'll have two angles, one acute, one obtuse angle, but you know the sine of two supplementary angles are equal, so it doesn't matter which angle you use. All right, okay. So the magnitude, first let's calculate the magnitude of the torque. The magnitude of the torque is the force times the distance times the sine of the angle. Okay, the force is 10, the distance is 1, and then you've got sine of 90, which is 1, right? So you get 10. Obviously the unit of torque is force times distance Newton meters. Okay, now we have to figure out whether it is positive or negative. So about this point, this force is going to rotate this way, which is counterclockwise. You see this direction is counterclockwise, so it's supposed to be positive. So we take the absolute value out and we make it positive. This is 10 Newton meters. So the positive means the effect of this torque is to produce counterclockwise rotation. Another example. Let's say you have this meter stick over here. Let's say it's pivoted at its center. Let's say this is 2 meters. Let's say this is 2 meters. Okay, now suppose we have this force over here, maybe 10 newtons, and this one's 30 degrees, and this is 1 meters. Okay, and the question is calculate the torque. This is this force. Calculate the torque. Okay, so what's RR? RR is the distance between the pivot and the point of application of force, right? So from here to here is 2, from here is 1, therefore this distance over here is 1. Okay, so our distance is 1 meters. Okay, the magnitude of the force, this one is 10 newtons. So the force is 10 newtons. How about the angle? You see this is a position vector of the point of application of force. So technically we're talking about this angle, but it doesn't matter whether it's this angle or is this angle, because the sine of the supplementary angles are equal. So just use 30 degree. All right, so you've got theta equals 30 degree. You can just see the smaller angle. Okay, so the magnitude of the torque now is force times distance times the sine of the angle, that is 10 times 1 for the distance, and then sine 30 for the angle. Okay, sine of theta is half, so you get 5 Newton meters. All right, now we have to figure out whether the tendency of this torque is to produce clockwise or counterclockwise rotation. You see, so what this force is doing is pulling it up, so it's going to rotate this way, which is counterclockwise, I mean clockwise. This is clockwise direction. Therefore, the torque is negative 5 Newton meters, okay, because its effect is to produce clockwise rotation. All right, let's look at another example. Suppose we have this lever, let's say it's 1 meter, let's say it's 1 meter, and then we apply force this way, let's say it's 10 newtons. All right, now as you can imagine, you cannot rotate this lever by applying force in the direction of the lever this way, right? So we expect the torque to be 0, but why is it 0 mathematically? Let's see. So what's the distance? The distance of the pivot and the point of application of force, R, is 1 meters. Okay, the magnitude of the force is 10 newtons. We've got F equals 10 newtons. Now let's look at the angle. You see, this is the angle, I mean the position vector. The position vector and the force are parallel, therefore the angle between them is 0. So you've got theta equals 0. That's why the torque is 0. So you've got the magnitude of the torque equals Fr sine of theta, and that equals 10 times 1 times the sine of 0. That is 0 Newton meters. Okay, so you cannot rotate a meter sig by applying force in this direction. The force has to have a component perpendicular to this position vector to rotate it. Okay, another example. How about if we have something like this? Let's say this is a pivot is over here. Let's say this is 1 meters. Let's say it's 1 meters, and then we're applying force right at the pivot. Okay, let's say this is 10 Newton. Okay, do you think you can rotate the meter sig by applying force at the pivot? You can't rotate it, so we expect the torque to be 0. Why is the torque 0 mathematically? Because you see the point of application and the pivot are the same point, so the distance between the pivot and the point of application of force is 0. So R is 0. This implies the torque is 0. Okay, so if either the force is parallel to position vector or the force is applied at the point of rotation, the torque is 0. Now next we're going to look at net torque. Net torque, that is, if you have a number of forces acting on an object, how do you calculate the torque? All it is, you calculate the torque with each force and you add them. Okay, so if there are a number of forces acting on an object, the net torque is the sum of all the torques due to the individual forces, Okay, so tau net, the net torque, simply is the sum of the torque with force 1, torque with force 2, torque with force 3, and so on. Okay, so that's how you calculate net torque. You just calculate the torque with each force and add them together. All right, now remember, torque is a vector quantity, but we're limiting ourselves to a one-dimensional case. In this case, one-dimensional case is a rotation in a single plane. Okay, when that's the case, you have only two possibilities, plus or minus. So this is plus for counterclockwise, minus for clockwise. So that's why we're writing this an algebraic equation. These are components of torque. Okay, they could be positive or negative. All right, let's demonstrate by means of an example. Suppose we have the following meter stick balanced at center of gravity. Okay, and let's say it's pivoted at its center of gravity. Let's say this is 2 meters, maybe a little longer, and then this is 2 meters, and we have the following forces. Maybe we have this one, let's call it F1, let's say is 10 newtons, and this angle over here is, let's say, 37 degrees. Maybe we have another force over here, let's say it's 5 newtons, and let's say this distance over here is 1 meters. Okay, and then we have other forces. Let's say this is F2, let's say this is F3, and let's say it is maybe 4 newtons. Okay, maybe we have another force over here. Let's say this is 0.5, and this force is, let's say, 3 newtons. Okay, so we want to calculate the net torque acting on this object. So to be sure, we have also 2 more forces. These are the 4 forces, F1, F2, F3, F4, but we have also forces over here. You see the fulcrum is pushing up, but its torque is 0 because that force is acting at the point of rotation. Okay, we have also another force, the weight of the meter stick, but this is balanced at the center of gravity, so that force also acts at the point of rotation. Its torque is 0. So the non-zero torques come only from these 4 forces. Okay, so we can say tau net equals the torque d force 1 plus the torque d2 force 2 plus the torque d2 force 3 plus the torque d2 force 4. Okay, so we're going to calculate these torques and add them up. Let's start with torque 1. Okay, let's start with torque 1. So its absolute value is F1 R1 sine theta 1. Okay, so F1, the magnitude is 10 Newton. Its distance is the distance between the point of rotation and the point of application of force, which is 2 meters. Okay, so R1 is 2 meters. How about the angle? The angle means this position vector and this force. Technically this angle, but it doesn't matter whether it's this angle or this angle over here. So that's 37 degrees. So you got theta 1 equals 37 degrees. So the magnitude of this is F1 is 10, and then R1 is 2, and then we got sine of 37. Sine of 37 is 0.6, so we get 12 Newton meter. And then we have to figure out whether it's positive or negative. So what's the effect of this force? Well, it's pulling up. So the effect of this force is to rotate this way, which is counterclockwise. So this torque is positive. So we have tau 1 is actually positive 12 Newton meters. Okay, let's do tau 2. Tau 2 is its absolute value is F2 R2 sine theta 2. Okay, this is F2, its magnitude is 5. So F2 is 5 Newton meters. Its distance, you see, is 1 meters. The distance between the pivot and the point of application of force is 1 meters. So you've got R2 equals 1 meters. How about the angle? You see, this is a position vector, this is a force, they're perpendicular to each other. Okay, so the angle is 90 degrees. So you've got theta 2 is 90 degrees. So we get this torque, its absolute value is 5 times the distance 1 times the sine of 90. Sine of 90 is 1, so we get 5 Newton meter. Okay, now let's see whether its effects produce clockwise or counterclockwise rotation. You see this force over here, its tendency is to rotate it this way, which is clockwise. Okay, so the torque is taken to be negative. So you've got tau 2 is negative 5 Newton meters. Okay, and then next we're going to do tau 3, the torque due to force 3, and that's going to be absolute value of tau 3 is going to be F3 R3 sine theta 3. Okay, so what is F3? This is our third force over here. Oh, this is our third force. This is our fourth force. Okay, this is our third force. So it is 4 newtons. The magnitude of the force is 4 newtons. The distance is the distance from here to here, which is 2 meters. Okay, the distance between this point and this point is 2 meters. So we have this is 2 meters. How about the angle? The angle is 90 degrees. The angle between this vector and this vector is 90 degrees. So you've got theta equals 90 degrees. All right. So the absolute value of the torque is the force, which is 4 newtons, the distance, which is 2, the angle, which is 90. Okay, so sine of 90 is 1. So we got 4 times 8. So this one is 8. Now we got to figure out whether it's positive or negative, or whether it's clockwise or counterclockwise. Okay, so we're talking about this force. You see, the effect of this force on this lever is rotated this way, which is clockwise. Okay, so it is negative. Therefore, this implies tau 2 is actually negative 8 Newton meter. Okay, and then finally we're going to tau 4. Okay, that the absolute value of tau 4 is going to be F4 R4, the sine of theta 4, and the magnitude of force is 3 newtons. So you've got F4 is 3 newtons. The distance between this point and this point, you see, from here to here is 2, from here is 0.5, therefore this distance is 2.5. Okay, so the distance for this one is 2.5 meters, and the angle between this vector over here, they're perpendicular to each other. The angle is 90 degrees. Okay, so the absolute value of tau 4 is 3 times the distance, which is 2.4, and then we have the angle 90 degree, sine of 90 degree. Okay, so this is 6 plus 1.5, that's 7.5. This equals 7.5 Newton meters, because this is 1. Okay, now we have to figure out if it's positive or negative. So the effect of this force is rotated this way, which is counterclockwise, right? Therefore it is positive. So we take tau 4 out, that is positive 75 Newton meters. All right, now we're ready to calculate the net torque. We've got tau net equals tau 1 plus tau 2 plus tau 3 plus tau 4. Okay, tau 1 is this is tau 1, which is 12. So this is 12. Tau 2 is -5. Tau 3 is -8. Tau 4 is 7.5. So that's it. So you've got 19.5 minus 13, which is 6.5. Okay, so this is 6.5. So it is positive. What does it mean? It is rotating clockwise. It's rotating counterclockwise. This implies it is rotating counterclockwise, because the torque is positive, because tau net is greater than 0. All right. All right. Now we're going to look at torque as a cross product. Torque as a cross product. The product. Now we just conclude that the magnitude of torque looks something like this. Magnitude of torque equals force times distance times sine theta. Now, if you look at this in terms of the force vector and position vector, do you remember any product? This formula is the magnitude of the product, the magnitude of the vectors and the sine of the angle in them. That is cross product. You remember? The cross product of A cross B is A times B times the sine of theta. You see, if you've got A, you've got B, and this is theta, that is the magnitude of cross product, which is basically the area of this parallelogram. Okay, the same thing over here. This is the magnitude of the cross product between the force vector and the position vectors. Okay, so what we have over here in this case is, let's say you have this point over here. Let's say the force is being applied maybe over here. This is a force. This is a position vector r. Okay, this is a force. Now, Fr sine theta is the area of this parallelogram. So it's basically the magnitude of the cross product between R and F. Okay, so this value actually represents the cross product between R and F. The cross between R and F is equal to the area of this parallelogram, which is equal to Fr sine theta. Okay, so if the magnitude of R cross F is actually equal to Fr sine theta. Okay, so the torque of a force is defined to be the cross product between position vector and force. Okay, so let's define now with this introduction. Let's define torque. Torque, that is now it's a vector quantity, is defined to be let me say torque with respect to a point. Torque with respect to a certain point is defined to be the cross product between the position vector of the point of application of the force, the point of application of the force with respect to point of the force with respect to the point and the force. Okay, so let's say we're trying to let's say the force is acting over here. This is F, and we're trying to calculate the torque of this force about this point. Okay, so this is a point of rotation. So we take the position vector of this point with respect to this point of rotation, and we call it R, and the torque of this force about this point is defined to be R cross F, as we're saying. So this is the point of rotation, and this is the position vector of the point of application of force, okay? Then the cross product between this position vector and the force gives you the torque of the force about this point. Okay, so this one you can say is point of application of force, and this is our origin, or you can say point of rotation. Okay, so that torque is defined as follows. Torque equals R cross F. This is the definition, the most general definition of torque. Torque is a vector quantity. Okay, so if you remember our discussion of cross product in the chapter of vectors, the magnitude of torque, is given by torque equals Rf sine theta, okay, where theta is angle between the position vector and the force. Okay, So it's the magnitude. Theta is angle between the position vector, or R and F. How about direction? If you remember, the direction of a cross product is perpendicular to the plane determined by the two vectors, right? So let's look at the direction. The direction is always perpendicular. The direction is always perpendicular to the plane determined by R and F. Okay, for example, let's say we're trying to calculate the torque of this force about this point. This is R, this is F, and then you can connect them tail to tail like this. So you got F over here, you got position vector over here. Okay, the plane determined by these two vectors, this is the position vector, this is the force vector, is the plane of the paper. So the direction of torque is either perpendicularly out or perpendicularly in. Okay, so that is, it's either perpendicularly out or perpendicular in to the plane determined by the two vectors. So to distinguish between the two possibilities, the two possibilities are perpendicularly out, which you remember is denoted by a dot, and perpendicularly in, which is represented by a cross. Okay, so if you remember, to distinguish the two, you can use either the screw rule or the right hand rule. Okay, the screw rule or the right hand rule can be used. The right hand rule can be used. Okay, so if using the screw rule, the screw should be rotated from the position vector toward the force. Okay, screw rule. I'm not going to discuss the details over here because we've already done it. So I'll just say rotate screw from R towards F. Okay, and then the direction of movement of the screw will give you the direction of the torque. Okay, how about the right hand rule? For the right hand rule, in this case, align index finger in the direction of position vector and middle finger in the direction of the force. So align index finger in the direction of position vector, okay, and align middle finger in the direction of force. Okay, then of course thumb gives you the direction of the torque, then thumb gives the direction of force, Okay, so that's if you're using the right hand rule. Let's say these are the position vector and the force connected tail to tail. Okay, so it's F over here. Now if you use the screw rule over here, you're going to rotate toward this, the force. Then you see when you rotate screw clockwise, it goes in. So the direction of the torque in this case is perpendicularly in, okay, across or perpendicularly in. If you use the right hand rule, remember this should be in the direction of the position vector, the index finger, and this is the middle finger in the direction of the force, and then thumb points down. Okay, so either case the direction is perpendicularly in. Okay. All right, so you calculate the magnitude of the torque using this formula, and then you can use the direction of the torque using either the right hand rule or the screw rule. Okay, let's consider an example. Suppose we have the following, let's say lever over here. Okay, so let's say this pivot over here. Let's say these are 1 meter, 1 meter, okay? And let's say this is a force, 4 Newton meters, okay? Suppose this is, let's say 30 degrees, all right? So the torque, whoever done this, I'm just to show you how to do the directions, okay? So what's the position vector over here? The position vector is the vector of the point of rotation with respect to the pivot, okay? So this is my position vector over here, and its length is 1 meters. And the torque, the force is going this way. This is my force over here, okay? Okay, so this is a force, this is a position vectors. But I got to connect them tail to tail, so when you connect them tail to tail, you get this one. This is the position vector, and the torque is going this way like this, okay? So this is a force over here. All right. Of course, the magnitude is F r sine theta, okay? So the magnitude is F r sine theta, which is, the force is 4, the distance is 1, the angle is 30. So we have 4, that's 4 Newton meters. That's the magnitude, all right? How about the direction? Well, if you decide to use the screw rule, you put your screw over here and rotate in this direction, right? Which is counterclockwise, which tells you the direction is perpendicularly out. Or if you want to use the right hand rule, you see it'll be like this. This is the position vector, this is the force, and thumb points up. So in either case, the direction is perpendicularly out, okay? So the direction is perpendicularly out. So usually, perpendicularly out corresponds to counterclockwise rotation, and perpendicularly in corresponds to clockwise rotation, okay? So perpendicular out means it's rotating in a counterclockwise, perpendicular out means it's rotating in a counterclockwise direction. Perpendicularly in means it's rotating in a clockwise direction. Actually, you can say that direction of torque, and direction of rotation are related by the right hand rule, okay? Direction of torque, and direction of rotation, that's whether it's clockwise or counterclockwise, are related by the right hand rule, are related by the right hand rule. The right hand rule, okay? So by the right hand rule, we mean something like this, If thumb is aligned in the direction of torque, then fingers give you the direction of rotation. So that is when thumb is aligned in the direction of torque, then fingers give you the direction of rotation. That's either clockwise or counterclockwise, the direction of rotation. Now let's say the direction of torque is perpendicularly up like this. So you see my fingers are rotating in a counterclockwise direction. But if the torque is down like this, sorry, if the thumb is down, then the finger's gonna clockwise direction, okay? So that's how you relate direction of torque and direction of rotation. But if you know the position vector and the force and the ij notation, you don't have to go through this. You can just use the cross product for vectors expressed in Cartesian unit vectors to do the torque, okay? So now let's look at for position vector and force expressed in terms of Cartesian unit vectors. Cartesian unit vectors, that is ijk, okay? That's ijk, okay? Suppose the position vector is x in the I plus y in the j plus z in the k, and let's say the force is fx in the I direction plus fy in the j direction plus fz in the k direction, okay? Now I'm not going to go into details, but we have already done this in a previous chapter. Then the r cross f is given by, in the I direction, we have, if this is x, then the y comes first, that's x, y, and then fz, okay, minus, and then you flip this two, this is fz, and then you've got z, and then you've got fy, okay, and then plus j, this is y, z comes next, and then you've got fx over here, and then you flip them, you've got x and fz, and then you've got the k direction, that's z, next comes x, okay, and then the other one is y, and then you flip them, you've got y fx, okay? So you can use this formula to calculate the torque. This will give you an expression for the torque in terms of ij notation, okay? But usually you can just distribute it if you know the cross product between the unit vectors. So let me revise very shortly the cross product between the unit vectors. As you know, the cross product between two identical vectors is 0. The reason is because the angle between them is 0, theta equals 0, okay? So this implies I cross I equals j cross j equals k cross k equals 0, okay? How about the cross product between two different vectors? And let me just remind you one rule about cross product. If you flip b and a, they become negatives of each other. You get b cross a, okay? So how about I cross j? I cross j, you see, well, its magnitude would be, let's look at the magnitude first. This is the magnitude of I, which is 1, the magnitude of j, which is 1, and the angle is 90 degrees, right? So sine of 90 is 1, so we get 1. So the magnitude of I cross j is 1. How about the direction? This is I, this is j, okay? If you use the scroll rule, you have to rotate it from I towards j. What happens? The screw, if you rotate counterclockwise, comes out. So the direction is k, okay? So the direction of I cross j is k. When you rotate the screw this way, it comes out. So its magnitude is 1, its direction is k, so it follows I cross j equals k. If you flip them, cross I, it just becomes negative k, okay? So when you cross two unit vectors, the result is usually the other unit vector. All I have to find out is if it is positive or negative. And if from I to J, if you're going in counterclockwise direction, it will be positive. If you're going clockwise direction, it will be negative. Okay, so this is between I and J. How about between, let's say we have J cross K. Okay, from J cross K, you're going in counterclockwise direction, right? So that's simply going to be I. If you flip them, that's clockwise direction, it will be negative I. Okay, how about if you take K and J? So when you go from I did J and K, so let's do I and K. When you go from K to I, you're going in a clockwise direction, so that gives you J. If you flip them, then you get negative J. Okay, to remember this easily, you can just use a unit circle like this. Let's put I over here, let's put J over here, let's put K over here. Okay, so I cross J, you see, that is counterclockwise, so that's going to be K. J cross K, that's counterclockwise, that's going to be I. Okay, K cross I, that's counterclockwise, that's going to be J. But if you go the other way, if you're coming from J towards I, okay, that's clockwise, so you get negative K. If you go from I towards K, that's counterclockwise, you get negative J. And if you go from K towards I, that is negative I. So you can remember we're supposed to be negative using this circle over here. All right? Okay, so let's consider an example. Now I just want to do what we've been doing so far using this formula over here. So suppose we have this meter stick over here. Okay, and this balance over here, let's say this is 1 meters, let's say this is 1 meters, and we have the following forces. Let's say this is 10 Newton, maybe this is 53 degrees, okay? Maybe we have 4 Newtons over here, okay? And maybe I have another force over here, which is 5 Newton, and let's say this angle is 37 degrees. All right, let's call this F1, F2, F3. So the question is calculate net torque. Okay, calculate net torque. This is balanced at the center of gravity, so we don't have to worry about the weight of the meter stick. Okay, so the net torque, which is a vector right now, it is R1 cross F1 for this one, plus R2 cross F2, plus R3 cross F3. Okay, so you just have to identify these vectors. Now this is R1. R1 is this vector over here. Okay, so R1 is 1 in the I direction, so that's I. Okay, how about F1? F1 is 10 cosine of 30. I mean cosine of 53 in the negative I direction, and then sine 53 in the J direction. This is cosine of 53 in the negative I direction plus 10 sine 53 degrees in the J direction. Okay, so F1 is cosine of 53 is 0.6, so it's going to be negative 6 in the I plus 8 in the J. Okay, how about R2? R2, you see this is our second force. So this is R2. R2 is this position vector over here. Okay, so that's in the negative I direction. So R2 is negative I direction. All right, how about F2? F2 is, you see, cos times 37 in the I direction, sin 37 in the J direction. So this is 5 times cosine of 37 in the I direction plus 5 sine 37 in the J direction. Okay, that is cosine of 37 is 0.8, so that's 4 in the I direction. Sine of 37 is 0.6, so that is 3 in the J direction. Okay, how about R3? R3 is this one. This is force 3, so it's R3, that's negative I. Okay, that's negative I. How about F3? F3 has only negative j component, okay? So that's negative 4 in the j. That's it. Now all I have to do is do the cross products, okay? So F net equals R1, which is I, cross it with F1, that's negative 6 in the I plus 8 in the j, negative 6 in the I plus 8 in the j, plus R2 is negative I, cross it with F2, F2 is 4I plus 3j, that is 4 in the I plus 3 in the j, and then we have R3 is also negative I, that is negative I, cross it with the force, which is negative 4j. Okay, that's all we have to do to calculate the torque. Okay, so we have I cross I is 0, so we didn't get any contribution from here. Okay, and then I cross j is k, so we get 8 in the k from the first term. Okay, how about this one? I cross I is 0, I cross j is k, but we have a negative over here, so that is negative 3k. Okay, plus I cross j is k, and we've got two negatives over here, so it's going to be positive, so this is plus 4 in the k. Okay, so that is 12 in the k minus 3 in the k, that is 9 in the k. What does k mean? Perpendicularly out, that means the direction is counterclockwise, that is the effect of the torque is to produce counterclockwise rotation. Okay, so tau net is 9k, okay, Newton meter. So the direction is perpendicularly out. Direction is perpendicularly out because that's positive k, and that also means counterclockwise rotation. Counterclockwise. Positive k is counterclockwise rotation. Okay, so k is counterclockwise, negative k is clockwise. Okay, so positive k is usually counterclockwise, and negative k is clockwise. So this is an example of doing the torque using the definition R cross F. All right, now we're going to look at torque per rotation about a fixed axis. Torque of a solid rotating about a fixed axis. Rotating about a fixed axis. Okay. So let's say you have this object over here, and it's allowed only to rotate about this axis over here. Okay, so if you got a tangential force acting on this object, okay, so let's say you have this is a perpendicular distance r perpendicular, so it's only the component of the force in this direction that's going to rotate it this way. Like, so suppose you have this force over here, so you take the tangential component of the force, okay, let's call this tangential force of the force. So the torque is simply the perpendicular distance times the component of the force perpendicular to this one, or tangential. Remember, this is rotating in us. If you take a certain point over here, it's rotating in a circular path. Okay, so the torque is determined by the circle over here. So this is the perpendicular distance. This is the component of the force perpendicular to this distance over here. Okay, so you can say torque is the perpendicular distance times the tangential component of the force. Okay, that's how you calculate torque. Perpendicular distance times the component of the force that is in the direction tangent to the circle. You see, if you take any point over here, it's rotating a circular path. So you take the component of the force tangent to that to the circle, and then times the radius of that circle will give you torque. Okay, so it is a product of the perpendicular distance and the tangential component of the force. All right, now we want to look at relationship between torque and angular acceleration. Torque and angular acceleration. In other words, we want to look at the formula equivalent to Newton's second law for rotations. Okay, so let's say this object is rotating about this x over here. So take a certain mass over here. Okay, let's call dm over here. Okay, so let's say this force over here is the tangential of the force acting over here. Let's call dft the force acting over here. Let's say this distance over here is r perpendicular. Okay, so this small mass over here dm is rotating in a circular path like this, right? So this is the component force in the direction of tangent to the circle over here, and this is the perpendicular distance. So the torque acting just on this mass, you can say d tau is r perpendicular times the force. Okay, well, we're talking about one-dimensional case, so let me take off the vectors. So we have d tau equals r perpendicular times dft. Okay, so the direction of torque is fixed, so we don't have to carry the vectors. But what is force? Force is mass times acceleration. Okay, so this force acting on this mass is its mass times its tangential acceleration, right? So we can say that the torque acting on that small mass element is its perpendicular distance from the axis of rotation, and the tangential force is the mass and the tangential acceleration. Okay, but if you remember, the tangential acceleration is the radius times angular acceleration, right? So you've got the torque acting on this object is r perpendicular dm, and then r perpendicular times angular acceleration, right? So you get dm r perpendicular squared times angular acceleration. And to get the total torque, you just integrate. Okay, so we have the integral of dm r perpendicular squared times alpha. Now remember, this perpendicular distance varies depending on where the mass is. Okay, if the mass is over here, the distance, so it's a function of where the mass is. So that is a variable, but the entire object is rotating with the same angular acceleration, right? So this is a constant, so we can take it out. So you've got torque equals alpha, the integral of dm r perpendicular squared. But if you remember, this is the definition of moment of inertia about the axis of rotation. This is moment of inertia about the axis of rotation. So we have the following formula: torque about a fixed axis equals moment of inertia times angular acceleration. So this is the formula relating torque and angular acceleration. Now compare this with Newton's second law. You see, force equals mass times acceleration. So force is to linear motion as torque is to rotational motion. A is to linear motion as angular motion is to rotational motion. So this tells you M is to linear motion as moment of inertia is to rotational motion. That's very important. Let's over here. Mass is to linear motion as moment of inertia inertia is to rotational motion. Rotational motion. All right. So what's important is this is moment of inertia about the axis of rotation. Okay. I is moment of inertia about the axis of rotation. Okay, let's look at an example. Let's say a sphere of radius, let's say 0.2 meters, and let's say mass 2 kilograms, is rotating about an axis tangent to the sphere, tangent to the sphere. Okay, if its angular speed change it, let's say from rest to 10 radians per second in 2 seconds. The question is calculate the torque acting on it. The torque acting on it. Okay, so there's a problem. We have a sphere. It's rotating about an axis that is tangent to the sphere, like this. Okay, so this is our axis of rotation. All right, and what else do we know? The mass is 2 kilograms. The radius is 0.2 meters, and the initial angular speed is 0. It started from rest. The final angular speed is 10, and the time taken for that is in 2 seconds. Okay, so we have to calculate the torque. The question is calculate the torque, question mark. But we know that torque is moment of inertia times angular acceleration. Okay, so we have to obtain both angular acceleration and moment of inertia. First, let's calculate angular acceleration. Angular acceleration is, if you remember, omega final minus omega initial divided by time taken. Okay, so the final is 10 minus 0 divided by 2. So the angular acceleration is 5 radian per second square. Okay, now the moment of inertia for the axis passing through center of mass can be obtained from textbooks, and that is ICM. This is moment of inertia about an axis passing through the center of mass, is 2/5 mr squared. But we need the moment of inertia about an axis passing through the tangent to the sphere, which is the distance of the radius over here. Okay, so how do we do that? You see, since these two axes are parallel, we can use the parallel axis theorem. Okay, if you remember, the parallel axis theorem states that moment of inertia equals moment of inertia by the center of mass plus the mass, and then the perpendicular distance between the two axes squared. Okay, so in this case, the mass is 2 kilograms. How about the distance? The distance is this, the perpendicular distance between the two axes. So the distance equals the radius in this case, which is 0.2 meters. Okay, so let's calculate the moment of inertia. So moment of inertia is, this one is 2/5 mass times r squared. That is the moment of inertia about an axis passing through the center of mass, and they've got m radius squared. Okay, so we can factor out mr squared, and then we have 2/5 plus 1/5/5. Okay, so the moment of inertia is 7/5 over 5 mr squared. Okay, so if you calculate that, that's going to be 7 over 5 times the mass 0. What's the mass? The mass is 2. So the mass is 2. Well, let me just do the radius and then times the mass. All right, so that is, from the numbers we have 4 times 2, 28 over 5, and then times 10 to the power of negative 2. All right, so that is the moment of inertia. All right, so we go back to the formula for the torque. The torque is moment of inertia times angular acceleration. Okay, the moment of inertia is 28 over 5 times 10 to the power negative 2, and the angular acceleration we just calculated is 5. So we get 28 times 10 to the power negative 2 Newton meter, or 0.28 Newton meters. Okay, so this is an example of using the relationship between torque and angular acceleration. Now we're going to look at another example. Suppose we have the following situation. Let's say we have a wheel and axle. A wheel and axle like this. So you have like this. Okay, and we have an object hanging from here. Let's say this is 10 kilograms. Okay, this is a disc, a cylinder, or you can say a disc in any case. The radius of the disc, let's say this over here, is 0.1 meters or 10 centimeters. Let's say the mass of the cylinder, is let's say 2 kilograms. Okay, so its radius 0.1 meters, its mass is 2 kilograms. That'll help us to calculate the moment of inertia of the cylinder. Okay, so this cylinder over here is rotating about an axis passing through the center of mass. Okay, and so we just need this formula for a cylinder. The moment of inertia about an axis passing through the center of mass is m r squared over 2. Okay, so we'll need this to calculate the moment of inertia. Now the question is, calculate the acceleration of the hanging object and the tension in the strain, and the tension in the strain. Okay, so we have two objects over here. One is moving linearly while the other one is rotating, so we have to do them separately. Okay, so first we're going to look at the linear motion of the hanging object. For linear motion, we have to use force equals mass times acceleration. For rotational motion, we have to use torque equals moment of inertia times angular acceleration. Okay, so first we're going to look at the linear motion of the hanging object. Linear motion of the hanging object. So what are the forces? You got the tension pulling up, you got the weight pulling down. Okay, let's call this mg. Okay, I'm going to use capital M for this one, small m for the mass of this object. Okay, so it's going down, so you can say that the weight minus the tension equals mass times acceleration. Okay, so that's the equation for this one. Net force equals mass times acceleration. You got force pulling down, tension pulling up, the difference equals mass times acceleration. So this is the equation for the linear motion of the of the object. And then we have to look at the rotational motion of the cylinder. Rotational motion of the cylinder. Okay, so there are two ways we can calculate the torque. We can say torque equals R perpendicular times the tangential force. Okay, so this is the force over here, which is the tension is tangent to the radius over here. So in this case, the perpendicular distance obviously is the radius of the cylinder. Okay, this one over here, radius equals 0.1 meters. Okay, the radius of the cylinder, and the tangential force that's rotating the object is the tension in the string. That is the tension in the string. So that's T. Okay, so we can say torque equals the radius times the tension, but also we can say it is moment of inertia times angular acceleration. Okay, so it's the axis passing per center of mass, so you can say ICM per cylinder. So we have this equation, R times T equals ICM times angular acceleration. But what does angular acceleration equals? It is linear acceleration divided by the radius. Okay, so you've got RT equals, this is for cylinder is mr squared over 2, the moment of inertia with the center of mass, and then we have linear acceleration divided by the radius. All right, so let's make simplifications. You see the radius will go out. You've got R over here, R squared over R, so the radius will go away. So you've got the tension equals m over 2 times acceleration. Okay, so we have two equations. Let's put them together. One is mg minus T equals ma, and then the other one is T equals m over 2 times a. Okay, so remember, this is mass of cylinder, this is mass of hanging object. Okay, let me write that again. M is mass of hanging object, which is 10 kilograms, hanging object. Okay, so you've got m equals 10 kilograms, and m is mass of cylinder. Mass of cylinder, which is, I think, 2 kilograms. 2 kilograms. Okay, this is 2 kilograms. Okay, so we can just plug in this over here to solve the equation. So you've got mg minus m over 2a equals ma. Okay, equals ma. So mg equals, we can factor out m plus m over 2a. Okay, so that's it. We plug the numbers. This is 10, gravity approximately 10, acceleration we don't know. This is 10, and this is 2 over 2, that's 11, so you've got 100 equals, that's 11a, so the acceleration is 100 over 11 meters per second squared. Okay, and then for the tension, we can use this formula over here. T equals m over 2 times a. Okay, so that is 100 over 11 divided by 2. No, the mass is 2. So you've got 2 over 2 times 100 over 11, which is 100 over 11. Oh, it's also 100 over 11 newtons. All right, that's it. All right. Another example. Now we're going to consider a cylinder rolling in an inclined plane like this. So you got this cylinder rolling, okay, and its radius, let's call it r over here. Let's say its radius once again is 0.1 meters. Let's say its mass is 2 kilograms, okay, and this is a sphere, okay, sphere. All right, so the question is to calculate the acceleration down the plane and the force of friction. The question is calculate its acceleration down the plane and the force of friction. Now remember, what is rotating? It is the force of friction. Okay, so we have two forces involved. The friction, you got the force of friction over here, but then we have gravity. Okay, this is mg, but remember the forces responsible for pulling in this direction is mg sine theta. Let's say this angle is 30 degrees. Okay, so it's going to be 9 minus theta. This component over here, if you remember, is mg sine theta. So this force over here is mg sine theta, which is a component of gravity in this direction. Okay, so we have two kinds of motion. It's moving linearly, but it's rotating also as it moves. So we're going to deal with the linear motion and rotational motion separately. Okay, so we're going to start from the linear motion. So for the linear motion, we have to use Newton's second law. F net equals mass times acceleration. Okay, so well, I'm using capital M in this problem. So what's the net force? The net force is this mg sine theta, which is sine theta over here, minus the force of friction. Okay, so this force is mg sine theta minus the force of friction equals mass times acceleration. So this is the equation from linear motion. Okay, where theta is the inclination angle. Okay, this one is theta over here. All right, how about rotational motion? Well, for rotational motion, we have to use the formula torque equals moment of inertia times angular acceleration. So torque equals moment of inertia times angular acceleration. Now it's rotating upon an axis through its center of mass, right? So we can say ICM over here. But we know that for a sphere, the moment of inertia of the center of mass is 2/5 mr squared, okay? And angular acceleration is linear acceleration divided by the radius, okay? So the torque is 2/5 mr squared times linear acceleration divided by the radius, okay? So the radius goes away, so we've got 2/5 mRA, okay? But also the torque is r perpendicular times tangential force, okay? So the r perpendicular in this case is the distance of the axis of rotation. The friction is acting at the edge over here, right? That's what's causing this rotation. So r perpendicular is the radius, and the tangential force causing the rotation is friction, okay? So we can also say torque equals radius times friction, okay? So this implies radius times friction equals 2/5 mRA. All right, so the radius goes away, so you got friction equals 2/5 radius times acceleration. Okay, so we have this equation. Now we're going to put both equations together. Okay, from linear motion we have mg sine theta minus friction equals mass times acceleration. That's from linear motion. And from rotational motion, we have friction equals 2 over 5 RA. 2 over 5 RA. Okay, so you just have to solve these two equations. Okay, so you've got, so we can substitute for F this one over here. So you've got mg sine theta minus 2 over 5 RA equals MA. Okay, so you've got mg, the sine of theta equals, is there a mass over here? Let me see. Oh, I'm sorry, I was supposed to cancel the R over here. The M is still over here. So this is MA, 2 over 5 MA. This is MA. This is MA. Okay. So this equals 2 over 5 plus 1 MA. Or that's 7 over 5 MA. Okay. So it follows that the acceleration, M cancels out, is 5 over 7 G sine theta, which is 5 over 7, gravity approximately 10, and then you've got sine of 30, which is half. So you've got 25 over 7 meters per second square. Okay. And now let's look at another example. Suppose you have the following situation. You have an object, let's say M1, maybe 2 kilograms, and then there is a pulley over here, which is a cylinder, let's say. So you have this object going through here, and then we have another object over here. Let's say it's M2 equals maybe 10 kilograms. And then this cylinder over here, M, let's say it is maybe 0.5 kilograms, okay? Let's say the radius of the cylinder over here, the radius of the cylinder, let's say it is 0.1 meters, okay? So let me just, capital M is mass of cylinder, this pulley over here, which is a cylinder, mass of the pulley, and R is radius of the pulley, radius of the pulley. Okay, so what do you have here? We have linear motion of this object, linear motion of object 2, and rotational motion of the cylinder over here, the pulley. All right, so we have to deal with all of them separately. Okay, so now what do we have? Let's say the tension over here is T1. Now for this to rotate, there should be a difference between the tensions. Okay, so these two cannot be equal. So let's say tension over here is T2. All right, so the question is to calculate the acceleration of the system, tension 1 and tension 2. The question is calculate the acceleration of the system, the acceleration of the system, tension 1 and tension 2. Okay, so we have to do the dynamics of these three objects: the sliding object, the hanging object, and the rotation of the pulley. This is the pulley. Okay. All right. First, I'm going to deal with the linear motion of sliding object. Sliding object. I'm going to assume no friction. Okay, no friction. No friction. All right. So what's the force acting on this object? Only this tension over here. You got normal force going to be balanced by the weight. So the equation for this one is T1 equals M1 times A. Okay. all of them will move with the same acceleration. All right, so this is linear motion of the sliding object. And then next, let's look at linear motion of hanging object. Linear motion of hanging object. That is Newton's second law. Okay. So what's the net force for the hanging object? You got M2G pulling down, and you got tension T2. Okay, so we can say M2G minus tension 2 equals its acceleration M2 times A. Okay, so this is linear motion of the hanging object. And then we have rotational motion of the pulley. Rotational motion of the pulley. Okay, so now the rotational motion, you see, is rotating this way, so T2 must be bigger than T1. So the torque T2 is T2 times the radius, okay? And the torque this T1 is T1 times the radius, okay? Do you see that? We have the pulley like this. Let me exaggerate over here, okay? So the force, the tangential force of the tensions, you got T2 on this side, you got T1 on this side, okay? The torque T2 is T2 times the radius, okay? Perpendicular distance times the force. The same thing over here, it is the radius times the tension T1. So the torque on this one is T2 times the radius minus T1 times the radius, okay? That also equals moment of inertia times angular acceleration. But the angular acceleration is acceleration divided by the radius, okay? So we have the following equation. T2 minus T1 times R equals the moment of inertia acceleration times R. Moment of inertia times acceleration divided by R. But it's rotating about an axis through its center, so this is ICM, okay? And for a cylinder, ICM equals mr squared over 2, okay? So you've got T2 minus T1 times R equals ICM is mr squared over 2 times A over R. So you see the R cancels out, so you've got you have one R, so you've got T2 minus T1 equals MA over 2, okay? So we have this equation. This is for the rotating cylinder, all right? So we have three equations. Let's put them together. We have T1 equals M1A. We have M2G minus T2 equals M2A. And then we have this equation, T2 minus T1 equals M over 2A. That's what we have to solve, okay? So, let's put two equations together first. Well, maybe I can put T1 equals M1A over here, okay? So you've got T2 minus M1A equals M over 2A, okay? I just replace the T1 by this one over here. So that gives you T2 equals M over 2 plus M1A, okay? So what is M? The mass of the cylinder. The mass of the cylinder is 0.5. So that is 0.5 over 2 plus the mass of the sliding object 2 times A. Okay, so you get the following equation. T2 equals, this is 2 and 1/4. So you've got 1 plus 8, that's 9 over 4. Okay, 9 over 4. All right, times A. All right. All right, so we have this for T2, and then you can plug that in here. Okay, and then solve for A. So you've got, I'm going to use this equation now. What's M2? The mass of the hanging object is 10 kilograms. So let me use the second equation. M2G minus T2 equals M2A. Okay, so we just concluded T2 is 9/4 times A. So you've got, this is 10 kilograms, approximately 10 over here, minus 9/4A, 9/4A equals M2 times A, and M2 is 10, right? M2 is 10, so you've got this equals 10A. Okay, so you've got 100 equals 9/4 plus 10 times A, and that is 40/4, 49/4. So this is, A is 4/49 times 100 meters per second square. Okay, this is 40/40. Well, that's 40/4. That's 49/4. So you cross multiply, get this one, 400 divided by 49. All right. So this is 400 divided by 49. If you approximate this by 50, it looks like approximately about 8 meters per second square. But then let's go back to T1 equals M1 times A. Okay, M1 is what? M1 is 2, so this is 2 times 400/49 newtons. And then we have an expression for T2. T2 equals 9/4 times A. That is 9/4 times, the acceleration is 400/49. So it'll be 900/49 newtons.